Okay, one more colligative property to talk about before we kind of get into what we can do experimentally with some of this data from colligative properties. And this one is called osmotic pressure. So osmosis, I think everybody learns about in high school science, is water, movement of water across a membrane. The water moves from areas of lower concentration to areas of higher concentration, right? Because the pressure will be equilibrated when the concentrations are equal on sides of the membrane. Well, there's a pressure associated with that movement, and we can calculate how much pressure there would be based on the concentration of the solution. So osmotic pressure, there's a formula here, and I have this one printed out on the page already. The osmotic pressure is symbolized by the capital Greek letter pi, so not quite as swoopy across the top and a little sturdier is the capital letter pi. Generally, we're going to measure the pressure in atmospheres here. Capital M here is molarity, so this will be the concentration in terms of moles per liter of our solution that we made. R here is the gas constant, so the same constant we used for gas laws. So 0.0821, and again, not a variable, just a constant. Liter atmospheres per Kelvin mole, right? And then the temperature here is Kelvin temperature. And so whatever the temperature is, we'll have to convert it to Kelvin. Now, if you ever find you're having some trouble figuring out what the formula is, all the information you need is right here. If you have your gas constant, right, liters and atmospheres over kelvins and moles, you've got to multiply by the temperature to get rid of kelvins. Got to multiply by the concentration in terms of molality units to get rid of liters and moles, and that will leave the pressure units that you want for your osmotic pressure. Okay, let's look at the first example here. Seawater contains 3.4 grams of salts for every liter of solution. Now, if we make the assumption that that's all sodium chloride, so we have a molar mass that we can use for the calculation, what would be the osmotic pressure of seawater if it's at 20 degrees Celsius? Okay, so we talked about needing molarity of the solution. So let's take that mass we were given. And if that's all sodium chloride, we could calculate how many moles of sodium chloride there are by using the molar mass of sodium chloride. So 1 mole of NaCl. If we add together those two components, so sodium has a molar mass of 22.99. Chlorine has a mass of 35.45. If we add those together, you get 58.44 for the molar mass of sodium chloride. So 1 mole of NaCl is 58.44 grams of NaCl. That will tell us how many moles of solute we have here. And that would be 0.05818 moles. Okay, now we're told in the problem that's for every liter of solution. So that's already per liter, so that's already molarity units. So once we have that, we can plug into our equation. This osmotic pressure is going to be equal to that molarity times our gas constant, right? And then times the temperature, but it's got to be Kelvin. So 20 degrees C, if we add 273, that would be 293 Kelvin. So just like gas laws, make sure you always convert your temperature to Kelvin here when you're doing this. Now, all we have to do now is multiply this out. Right? And it comes out to 1.3995. Now, going all the way back to our mass, there's only 2 sig figs, so I'll round that to 2 sig figs. That would be 1.4 atmospheres would be the osmotic pressure for that solution. Of course, you can see from the equation, if the concentration would go up, the pressure would go up, right? If everything else stays the same. Temperature goes up, the pressure would go up at the same concentration. Okay. Now, we want to look at what we can do with some of this information from colligative properties. One of the more common uses of colligative properties, since it's only based on how many pieces are present, in terms of the size of the effect and change on that physical property, Because colligative properties can be used to determine the molar mass of an unknown compound. And since every colligative property we looked at has a link to concentration, we can get to moles from the equations that we looked at, which is exactly what we want to do. So let's look at this problem. So if we have this compound, lauryl alcohol, that comes from coconut oil, actually used in things like soaps and detergents. We take 5 grams of lauryl alcohol, dissolve it in a certain amount of solvent, so 0.1 kilogram of benzene. We measure its freezing point, so we measure where it's going to freeze. We compare that to the freezing point of the pure solvent. We use the freezing point depression constant. We can figure out what the concentration of that solution is. Right? From there, we need to pull out how many moles. So let's go ahead and try to figure out what the concentration of this solution is. If the new freezing point is 4.1 degrees C, but the initial freezing point was 5.5 degrees C, that means the freezing point is changing by negative 1.4 degrees Celsius. That's the temperature change of the freezing point. Now, our freezing point depression formula was the change in temperature is equal to the constant times the molality. If I divide through by the constant, because we're trying to solve for concentration here, or molality, right? We can get molality by itself on one side of the equation. If I plug in the change in temperature, along with the constant that was given in the problem, right? Now I'm going to have the concentration of the solution, or its molality. So that comes out to be 0.2734, right, molals. Now, important step here, we want to use this number to get to how many moles of solid were in the solution. This is not moles, although that's a very common mistake when people are looking at this problem. We need to remember what molality actually stands for. This molality tells us how many moles of solute are present in every kilogram of the solvent. So this is only how many moles are in there if we used 1 kilogram of solvent. If we didn't use 1 kilogram of solvent, we need to cancel out the units on the bottom of this relationship. So in this case, when we did the experiment, we used 1/10 of a kilogram of solvent. So if I multiply by how much solvent was used, 0.1 kilogram, that's going to cancel out the units that we want to get rid of there. That'll just leave us with moles of solute. Now multiplying by 0.1 is just going to move the decimal, so I don't need to plug that into the calculator. It'll be 0.02734 moles, right, of our solid, the lauryl alcohol in this case. Now that's still not quite the answer. We were looking for molar mass. So molar mass, you should remember from first semester chemistry, is measured in grams per mole. We did this experiment. We know how much lauryl alcohol was measured out, 5 grams. Based on the change from the colligative property, we can calculate how many moles were in that sample. So if we take the mass and divide by how many moles there are, that gives us the right units to describe molar mass. So 5 divided by 0.02734, right? And that gives us 182.88 grams per mole. Now, if we do look carefully back at the problem, our temperature change here is fairly small. That's going to limit us to 2 significant figures. So we should really report this as 180 grams per mole with no decimal after the 0 to indicate, right, how precise our measurements are there in that calculation.